Today in this module, we will learn about two discrete probability distributions, namely binomial distribution and multinomial distribution. We will know the meaning of Bernoulli or binomial and multinomial random variable and experiment. In this module, we would also learn how the binomial experiment is different from the multinomial experiment. You would also learn how to compute probabilities for both the binomial and multinomial random variables using the associated probability distributions. For the former, we will also learn computing probabilities using binomial tables. In the end, we would also learn about the mean and variance values for both the distributions. I am sure you know that in real life we come across many situations whereby one of the two or more possible outcomes occurs. For example, flipping a coin will lead to occurrence of a head or tail. Similarly, children afflicted with a bacterial infection might respond to antibiotics medicine or not. Or a person appearing in an entrance examination will fail or pass, and so on. We can have very many examples of situations where we have two possible outcomes. So these are all instances of two possible outcomes of which either of them can be labeled as a success and the other as a failure. There are situations which can result in more than two outcomes, such as throwing a dice can result in any of the 6 possible outcomes. Similarly, drawing a ball from a container consisting of 4 colored balls can give any of the 4 possible outcomes. In the former situations, which means in the case of dice, where there are 2 possible outcomes, the binomial distribution is applied to compute the probability of observing a specified number of successes when the process is repeated a given number of times. In the latter applications, where more than 2 outcomes are possible, multinomial distribution is appropriate. So let's look at the derivation of the binomial distribution. The binomial distribution is the most popular discrete distribution or discrete probability distribution which is widely applied in business and in natural sciences and in medical research also. But we begin with the Bernoulli trial. As mentioned in practice, we often come across situations where there are only 2 possible outcomes. As we said, for example, a person entering in a shop will make a purchase or not, or a person suffering from a dreaded disease will survive or not, or a tube light coming off an assembling line may be defective or non-defective, and so on. Now, based upon the nature of the problem to be studied, out of the 2, we may define either outcome as a success and other as a failure. Now, this is known as a binary variable, and each trial in this is known as a Bernoulli trial. Now, this is named after a Swiss mathematician, Jacob Bernoulli, whose lifespan was from 1654 to 1705. He was one of the earliest mathematicians to develop probability formulas and techniques to study binary variables. Originally, Bernoulli described the 2 possible outcomes which could take values 0 and 1. The value 1 was labeled as success and 0 as failure, with p and 1 minus p as their respective probabilities. Accordingly, the density function of a Bernoulli trial can be written as px is equal to 1 minus p if x is equal to 0, and it takes the value p if x is equal to 1. Now, this can be written as p raised to power x into 1 minus p raised to power 1 minus x. The expected value or mean of the Bernoulli trial is defined as expected value of x, which is, I am sure you know, is nothing but equal to summation xi pi, and this in the current example will be equal to 0 into 1 minus p, where 0 is, I am sure you can see, is the value of x, and 1 minus p is the corresponding probability, plus 1 into p, where 1 is again the value of x, because x takes two values 0 and 1, and the corresponding probabilities are 1 minus p and p. So if you multiply 0 with 1 minus p and 1 with p, the expected value comes out to be equal to p. Similarly, let us find out the variance of the Bernoulli trial. Variance is defined as equal to expected value of x minus mu square, where mu is the mean of x. In the current Bernoulli trial example, this comes out to be equal to 0 minus p square into 1 minus p plus 1 minus p square into p. On summation, this is or on simplification, this is equal to p square into 1 minus p plus 1 minus 2p plus p square into p. Now, this on opening up the brackets gives us p square minus p cube plus p minus 2p square plus p cube, and is equal to p minus p square, and is equal to p into 1 minus p. So what we have proved is that the expected value of x, which where x is a Bernoulli trial, is equal to p, and the variance of this Bernoulli trial is p into 1 minus p. So this means, for example, if the probability of success p is equal to 0.6, then with Bernoulli trial, the mean of the distribution is equal to p equal to 0.6, and variance is equal to 0.6 into 0.4, and is equal to therefore 0.24. Let us understand the Bernoulli process and the binomial random variable. Now, consider an experiment that has the following properties. First, it consists of repeated number of identical trials, let's say n, which are fixed beforehand. So n is fixed before the trials. Each trial is a dichotomous trial, which means it can result in only two possible outcomes, which are referred to as success S or a failure F. Then the third is that the trials are independent of each other, which means the outcome of any one trial does not affect the outcome of any other trial. Outcomes are mutually exclusive in each trial. The fourth and the final is that the probability of success and failure, denoted by P and Q respectively, remains constant from trial to trial. So which means in each trial the probability of success is P and the probability of failure is Q. The outcome of any experiment consisting of repeated trials satisfying the above four properties is called a Bernoulli process or a binomial experiment. These Bernoulli processes furnishes a basis for the derivation of the binomial distribution. In fact, the binomial distribution is considered as a series of repeated independent Bernoulli trials. I am sure you can make it out clearly. Further, let's say x is equal to number of successes in n Bernoulli trials is called a binomial random variable. Now, since x can take only finite values such as 0, 1, 2 up to n, it is called a discrete random variable. For example, suppose a shopkeeper knows from his past experience that the probability of any person who enters his shop on any given day makes a purchase is 0.6. That implies the probability of any person not making a purchase is 0.4. Our interest lies in computing the probability of an experiment outcome that involves, say, 2 persons making a purchase if 10 persons enter a shop on a given day. So firstly, checking 4 requirements for a Bernoulli experiment, we note that the experiment consists of number of persons entering into a shop, which is fixed in advance, let's say n equal to 10 in our current example. Then there are only 2 possible outcomes, making a purchase, which can be considered as a success, or not making a purchase, which is defined as a failure. Third, we know that the probability of a person making or not making a purchase is assumed to be constant for all customers. And fourth, the purchase decision of one person is independent of the purchase decisions of other persons who enter the shop. So since all the above mentioned four properties are present in this experiment, it can be termed as a binomial experiment. And an outcome, two persons making a purchase out of 10, is a binomial random variable. Let us consider another experiment. Say a container consisting of 30 balls, of which 9 are of red color and the rest are of white color. So let 5 balls are drawn one by one without replacement. Let us label the ith ball a success S if the ith ball drawn is red in color. If not, let us label it as a failure F. Now finding probabilities of S in various trials, we can write down that probability of S on first ball drawn is equal to 9 upon 30 and is equal to 0.3, as there are only 9 red balls out of the 30 total balls. Similarly, probability of S on the second drawn ball or second ball drawn, it can occur with two possibilities, S on both the first and the second trial, or F on the first trial and S on the second trial. So we can write it down as probability SS plus probability Fs. Now this is equal to probability of S on the first ball into probability of S on the second trial given S on the first ball, plus probability of F on the first ball and or into probability of S on the second trial given F on the first ball. Now this is equal to 9 by 30 into 8 by 29 plus 21 by 30 into 9 by 29, and this comes out to be equal to 9 upon 30 into 8 by 29 plus 21 by 29, which is equal to 9 upon 30 and is equal to 0.3. However, in this experiment, we must notice that the trials of drawing a red ball are not independent, because, or for example, the probability of S on the fifth trial depends on the outcomes that have occurred on the earlier 4 trials. Considering only the two following possibilities: probability of S on the fifth ball drawn given S on the first, second, third and fourth ball. Now this will be equal to 5 upon 26 and is equal to 0.192. Whereas probability of S on the fifth ball drawn given F on the first, second, third and fourth ball is equal to 9 upon 26, which is equal to 0.346. What we observe from this example here is that trials are interdependent. The probability changes depending upon the outcomes in the previous trials. So this experiment does not follow the binomial distribution. If each ball had been replaced after being drawn from the container, then trials would have been independent. However, if the size of the population had been very large, let's say 3 lakhs, with number of red balls equal to 90,000, then probability of S again is equal to 0.3, 90,000 divided by 3 lakhs. Then the trial of getting red balls out of 5 balls drawn, regardless of the balls being replaced after the draw or not, would not have altered the probability very significantly. So probability of S on the fifth ball drawn given S on first, second, third and fourth ball, in that case will come out to be equal to 89995, which is 89,995 upon 299995 and is equal to 0.2999 and is approximately equal to 0.3. And the probability of S on the fifth ball drawn given F on first, second and third and fourth ball is equal to 90,000 upon 2,99,995 and is equal to 0.3 approximately. So hence trials of drawing balls can be regarded as being independent with constant probability Ps equal to 0.3 in this case. Consequently, the experiment can be considered as a binomial with fixed n equal to 5 and probability of success s equal to 0.3. Thus, in deciding whether an experiment with replacement can be considered as binomial, we follow a simple rule of thumb. What is that? That is that if the sample size or number of trials n is equal to or less than 5% of the population size, that means small n upon capital N is less than or equal to 0.05, where n is the size of the population, the experiment can be regarded as a binomial experiment. This is because we can see that the computed probabilities based on without replacement experiment are very close, almost the same to the probabilities based on the binomial experiment. In the experiment above which we have done, the sample size n is equal to 5 and small n upon capital N is 5 upon 3 lakhs and is equal to 0.4 times 0.167, which is much less than or equal to 0.05. Therefore, it can easily be approximated as a binomial experiment. However, earlier when n is equal to 5 and n upon n, which is small n upon capital N, is 5 upon 30, which is equal to 0.167, then we find this is greater than or equal to 0.05. And therefore, the probability of success was not constant, so it cannot be approximated by a binomial experiment. So students, I hope you understand that when can we consider an experiment as a binomial experiment and when it is not a binomial experiment. I am sure you should be very clear and remember and understand this rule of thumb for this. Let us now therefore go into some more details about this binomial distribution. The number of successes denoted as xi in a binomial experiment consisting of n trials is defined as a binomial random variable. The values that x can take in an n trial experiment are x equal to 0, 1, 2 up to small n. The probability associated with different values of this discrete random variable is called the binomial probability distribution. The distribution has two parameters, n the number of trials and p the probability of success. Therefore, it is denoted as x distributed binomially with n and p as the binomial distribution's parameters. So n and p are the parameters, which means if n and p are known, we can find out the binomial distribution and the binomial distribution probabilities. So suppose in our above example, balls being drawn with replacement and n is equal to 3, then x can take 4 values 0, 1, 2, 3. And there are 8 possible outcomes or 8 ways in which this may happen, and these are FFF, which means failure, 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 or FFS, FSF, SFFF, SSF, SFS, FSS, and finally SSS, which means all 3 successes. From the definition of x, and given that probability of S is equal to P and probability of F is equal to 1 minus P, the probability for each possible outcome can be written as probability of x equal to 0 is equal to probability of FFF is equal to probability of F into probability of F into probability of F, because please remember each outcome is independent of each other, and therefore it is equal to 1 minus P into 1 minus P into 1 minus P, hence is equal to 1 minus P to the power 3 or 1 minus P cube. Now this is, as I said earlier, is because the trials are independent and probability of success or failure in each trial is constant. Similarly, if we define or if we want to know the probability of x equal to 1, then it has three possible situations, and therefore the probability or the required probability would be equal to probability of FFS or FSF or SFF, which means success could be either in the third trial or in the second trial or in the first trial. All three are the desirable outcomes. Now, this is equal to probability of FFS plus probability of FSF plus probability of SFF. Now, this is equal to 1 minus P into 1 minus P into P plus 1 minus P into P into 1 minus P plus P into 1 minus P into 1 minus P, or this is equal to 3 into P into 1 minus P square. Now, there are three outcomes with x equal to 1, and each outcome has the same probability P into 1 minus P whole square. Though the order of S and F differs, which is of no importance, because whether success occurs in first trial or second or third, in a way it does not matter. Therefore, we can write this probability as the number of times an outcome is repeated into the probability of any outcome with x equal to 1. Similarly, we can find out probability of x equal to 2 and see what are the possible outcomes, which are SSF, SFS and FSS. And therefore, the corresponding probabilities are equal to probability of SSF plus probability of SFS plus probability of FSS. And I am sure you can see that this now will be equal to P into 1 minus P plus P into 1 minus P into P plus 1 minus P into P, which is equal to 3P square into 1 minus P, because you know there are three possible outcomes for x equal to 2. But now if you want to find out probability of x equal to 3, then we have only one possible outcome, which is SSS, and therefore is equal to probability of SSS, and this is equal to P into P and is equal to PQ, because as I said there is only one possible outcome. So we find that the probability of any outcome depends on the number of S, which means value that x takes, and the number of trials n, and the probability of success, which is probability of S equal to P. Therefore, the probability mass function, which is also written as PMF of binomial random variable, is written as B, in the bracket we write down x semicolon n comma P, which means it is the binomial distribution of x with n and p as the parameters. For example, the probability of x equal to 1 when n is equal to 3 and probability of s is equal to p can be written as probability of x equal to 1 is equal to b, in the bracket we can write down 1, 3 and p, and which we have already seen is equal to 3p into 1 minus p whole square. So in general we can write that b or the binomial distribution of x given n and p is equal to the number of outcomes with x success in n trials into the probability of any one outcome with x successes. This we can define as our equation 1. Further, since the ordering of S and F's doesn't matter, which means of success and failure doesn't matter, as you have seen in our example, the second term, which is the latter term in the above equation 1, which means the probability of any one outcome with x successes can also be written as probability of or p raised to power x into 1 minus p raised to power n minus x. For example, probability of x equal to 2 is equal to 3p raised to power x equal to 2 into 1 minus p raised to power n minus x, which is 3 minus 2 in our current example. And therefore, we had obtained 3p square into 1 minus p whole raised to power 1. So, as regards the first term in equation 1, the number of outcomes with x successes in n trials it can be interpreted as the number of ways of selecting x items, in our current case successes, in n objects which are also defined as trials. So it is same as the number of combinations that can be formed with n objects when x are chosen at a time. Now this can be written as NCX, or simply n and x, we can have them in the bracket, which is also a same way of writing as NCX. Now it is equal to, I am sure you know that NCX is equal to n factorial upon x factorial into n minus x factorial, where n factorial, which is read as n factorial, is equal to n into n minus 1 into n minus 2, so on up to 1. Similarly, x factorial is equal to x into x minus 1 into x minus 2 into x minus 3, so on up to 1. So generalizing this, we can write the probability distribution function of a binomial random variable x is where it is the number of successes with n trials and probability of s equal to p and probability of f equal to 1 minus p or q. It is b of x with n and p as the parameters equal to ncx into px into 1 minus p raised to power n minus x. And again I can elaborate and say that this is equal to n factorial upon x factorial into n minus x factorial into p raised to power x into q raised to power n minus x. This is when we have the x successes, or x is equal to 1 to n. However, this will be equal to 0 if we have otherwise. Otherwise means when x does not take these values from any of these 1 to n. So in particular, when n is equal to 5 and p is equal to 0.3 and 1 minus p is equal to 0.7, the probability when x is equal to 3 can be written as b of 3 with 5 and 0.3 as parameters and is equal to 5c3 into 0.3 raised to power 3 into 1 minus 0.3 raised to the power 5 minus 3 equal to 2. On simplification, this comes out to be equal to 5 factorial upon 3 factorial into 5 minus 3 factorial into 0.3 raised to power 3 into 0.7 raised to power 2. So you can solve these values and simplify and find out the required probability. For an experiment with n trials, binomial random variable x takes values 0, 1, 2, n, which means there are n plus 1 values that x can take. Further, since it is a probability function, the sum of the probabilities for all values that x can take should be equal to 1, which means we are saying that summation x from 0 to n of the binomial distribution b with variate x and parameters n and p must be equal to 1. We also know that the n plus 1 terms in the binomial expansion of p plus q raised to power n corresponds to the probabilities associated with various values that x can take, which means when x can take values from 0 to n in a binomial experiment of n trials. So that is we know, and what we are saying is this, that the p plus q raised to power n is nothing but equal to nc0 into p0 into q raised to power n plus nc1 p raised to power 1 q raised to power n minus 1 plus nc2 p raised to power 2 q raised to power n minus 2, so on up to ncn p raised to power n q raised to power 0. Now this can also be rewritten as equal to b of 0 np plus b1 np, so on up to bn np, which means it is nothing but the summation of bx given n and p, where x ranges from 0 to n. Now, since p plus q is equal to 1, we can see that p plus q raised to power n is also equal to 1 raised to power n and hence is equal to 1. So, we can say that the sum of all these probabilities has to be equal to 1. Now, this result is frequently used in finding probabilities such as probability of x less than or equal to x, where the first x is capital X, which means a particular value of the variate or the variate x, and this variate takes a value less than or equal to a particular value small x, or the reverse, which means the probability of capital X greater than or equal to small x. So, let me remind you again, capital X here is the variate value and small x is a specific value of this variate capital X. In the experiment which we have discussed above of drawing 3 balls with replacement from a bag with probability of red ball equal to 0.3 and probability of white ball equal to 0.7, the probability distribution for number of red balls out of 3 balls drawn is shown in a table. In this table, which is designated or titled as probability distribution of number of red balls drawn, which is our x variate in 3 trials. So, when capital X is equal to small x, where it takes value 0, 1, 2, 3, we can see we have written these probabilities based on the 2 parameters of p and n is 3 and p is equal to 0.3. So, we have 3c 0, 0.3 raised to power 0 into 0.7 raised to power 3, and it comes out to be 0.343. This is the probability of, in a way, 0 red ball drawn. Similarly, for 1, it comes out to be 0.441. For 2 or small x equal to 2, we get the probability 0.189, and for 3, we get the probability 0.027. If you add all these probabilities, I am sure you can see that the sum total comes out to be equal to 1, which is the sum of these 4 probabilities. So, this probability distribution corresponds to various values that binomial random variable x can take, and therefore it is called the binomial probability distribution. Let us take some examples. The example 1 is that suppose a shopkeeper knows from his past experience that the probability of any person who enters his shop on any given day makes a purchase is 0.6, which we have said earlier also. It is just a structured example. So, on any given day 10 persons entered his shop. Find the probability that what is the probability that each person or 1 person or 2 persons etc. they buy or they make purchases. So, what is the solution? That 3 persons made a purchase. We know that if x is equal to number of persons make a purchase, x is a binomial distribution where x in this binomial distribution n is 10 and the probability is 0.6. So, what will be the probability that x is equal to 3? The probability that x is equal to 3 is 10c3 into 0.6 raised to power 3 into 0.4 raised to power 10 minus 3 equal to 7. If you solve this, it comes out to be equal to 0.04247. Similarly, suppose we want to find out that at least 4 persons make a purchase, which means we want to find out probability that capital X is greater than or equal to 4. Now, this is same as equal to probability that capital X is equal to 4 or plus it is equal to 5 plus it is equal to 6, so on up to probability that X is equal to 10, which means it is a summation of X or X ranging from 4 to 10 of the binomial distribution of this variate X with 10 as n and p equal to 0.6. Now, this you can find out is also equal to 1 minus the probability that x takes the value 1 plus x takes the value 2 plus x takes the value 3. Now, you can therefore calculate it by this method also. because in this we will have to just find out that there is no purchase 0, 1 and 2 and 3. So just 4 values you have to find out rather than the 6 values in the remaining case. In fact, these will be how many? 4, 5, 6, 7, 8, 9, 10. 7 values you will have to calculate, not 6. So this comes out to be equal to 1 minus summation of x from 0 to 3 of b or binomial distribution of x with 10 and 0.6 as the parameters. Now this is equal to 1 minus 10c0 into 0.6 raised to power 0 into 0.4 raised to power 10 plus 10c1 into 0.6 raised to power 1 plus 0.4 raised to power 9 plus 10c2 into 0.6 raised to power 2 plus 0.4 raised to power 8 plus 10c3 into 0.6 raised to power 3 plus 0.4 raised to power 7. Now on simplification, this comes out to be equal to 1 minus 0.055, hence is equal to 0.945. So what we are saying is that the probability that at least 4 persons make a purchase is equal to 0.945. Similarly, we can have another example where we may say that at most 3 persons make a purchase, which can be written as probability x is equal to or 3 or less than 3. Now, which is same as probability of x equal to 3 plus probability of x equal to 2 plus probability of x equal to 1 plus probability of x equal to 0. And hence, I am sure you can make out this is again equal to summation of the binomial distribution of x with n, 10 and 0.6 as our probability, where x ranges from 0 to 3. And this is also equal to, in a way, what we said earlier is being repeated here, 1 minus the summation of x from 4 to 10 of the binomial distribution here. And since we have already calculated the second part, which was 0.945, so now the required probability is equal to 1 minus 0.945, which is equal to 0.055. So we can use the previous calculations of either the first part or the second part and calculate these probabilities. Let us now try to understand how do we find probability with binomial tables. Let us look at and try to understand these tables. Often you will find that computation of probabilities become very tedious, especially when n is large. Table A1 attached at the end of this module you will find tabulates the cumulative distribution function known as CDF, which is defined as f of x equal to probability that capital X takes the value less than or equal to small x, which means the variate takes the value less than or equal to a given value of x with selected values of n in combination with various values of p. For a given binomial random variable x with the specified values of n and p, the cumulative distribution function will be denoted by capital B with variate x and n and p as the parameters, and is defined to be equal to probability that capital X is less than or equal to small x. Let me repeat, where we have said capital X is the variate and small x is the specific value. Now this will be equal to summation of capital X from 0 to small x of the binomial distribution B with capital X and n and p as the parameters, and this x takes the values from 0 to small n, where n is the maximum number of trials. Let us take a second example to understand the similar thing. Suppose from the hospital records it is found that 30% of the cancer patients who undergo chemotherapy survive after the treatment. If 20 patients are admitted in a month, what is the probability that, let's say, A, at most 8 patients survive? So what is the solution of this? Which means we want to find out probability that capital X is less than or equal to 8. Now this will be equal to summation of B or binomial distribution, where we can define a new variate y and 20 and 0.3 as the parameters, and this y can now take the values from 0 to 8, where we are defining y as the number of patients who we want to be surviving or to survive. Now this is equal to capital B, 8, 20 and 0.3. So which is, how do you read this? This basically means that we are saying it is a cumulative distribution function of 8 as the variate value and 20 as the number of observations n and 0.3 as the probability of success. Now this probability can be found using D, the part of the binomial tables A1 that corresponds to n is equal to 20. Now within this portion of the table, the entry in the cell corresponding to the intersection of p equal to 0.3 and x equal to 8 gives B 8, 20, 0.3 equal to 0.887. So our required probability is equal to 0.887. Let's take the second possibility. Suppose we want to find out exactly 10 patients survive. Now this is not directly available from the table. Rather, we find CDF corresponding to x equal to 10. That is capital B of 10, 20 and 0.3, which gives us probability x less than or equal to 10, and at x equal to 9, that is beta of or B of 9, 20 and 0.3, which gives us probability of x less than or equal to 9. Then subtracting latter from the former, we obtain the required probability. So what we are saying is this, or it can be written as that probability of x equal to 10, which is exactly 10, is equal to probability that x is less than or equal to 10 minus probability that x is less than or equal to 9. And therefore, this is equal to capital B 10, 20, 0.3 minus B 9, 20, 0.3. And this comes out to be equal to 0.983 minus 0.952. Hence, the required probability is 0.031. Similarly, suppose we want to find out that at least 8 persons survive. Then what we want is that the probability capital X is greater than or equal to 8, which is same as 1 minus probability of capital X being less than or equal to 7. Hence is equal to 1 minus probability of X less than or equal to 7. And this again, if you express in terms of our distribution functions in terms of capital B, this can be written as 1 minus capital B 7, 20 and 0.3 in the brackets. And this is equal to 1 minus 0.772 equal to 0.228. This value 0.772 again has been obtained from the table corresponding to n equal to 20 and p equal to 0.3 with the success x equal to 7. Similarly, we are including both 5 to 8, that between 5 to 8 people survive, then this will be equal to probability that capital X takes the value greater than or equal to 5 but less than or equal to 8. Which means, in a way, we want to find out the probability that capital X or X takes the value 5, 6, 7 and 8. Now this will be equal to probability that X takes the value less than or equal to 8 minus probability X takes the value less than equal to 4. And hence this can be again from the tables calculated, and we find that this comes out to be equal to probability of or the cumulative distribution function of 8, 20 and 0.3 minus cumulative distribution function of 4, 20 and 0.3, and the table gives us values of 0.887 minus 0.238, and this comes out to be equal to 0.649. So with the help of this example, we have tried to explain how we can use the tables to find out the required probabilities. Having understood this, let us now look at the characteristics of the binomial distribution. A binomial distribution is fully specified if the number of trials n and the probability of success p are given. Therefore, for every given set of parameters, a particular binomial probability distribution can be generated. The shape, mean and variability of the distribution entirely depends on these parameters values, which means n and p. So what we are saying is, if you change n or p or both, you will have a different distribution and the different shape of the binomial distribution. What is the shape of the binomial distribution? The binomial distribution can be symmetrical or non-symmetrical in shape. Regardless of the value of n, it is the value of p that determines the shape of the distribution. If p is equal to 0.5, the distribution is symmetrical, and if p is not equal to 0.5, the distribution is skewed. For a given value of n, if p is less than 0.5, the distribution is skewed to the right, and if p is greater than 0.5, it is skewed to the left. However, the degree of skewness depends on how large is the value of n and how close is the p to 0.5. The larger the value of n and the closer the p is to 0.5, less skewed will be the distribution, or we are saying it will be more symmetrical. What are the mean and variances of the binomial distribution? Let us try to understand and find them out. Let the outcome of the ith trial signifies a Bernoulli trial, which can assume value 0 with 1 minus p as the probability and 1 with p as the probability. So two possible outcomes, 0 and 1, with corresponding probabilities 1 minus p and p. I am sure you would recollect 0 also we have defined as failure and 1 as success. Then the number of successes x in n independent trials can be considered as a sum, which means we can consider capital X equal to x1 plus x2 up to xn, where each xi is a Bernoulli variable with expectation p. Thus, the expectation or mean of a binomial variable may be thought of as the sum of expectations of the n Bernoulli variables. Hence, we are saying the expected value of capital X is equal to expected value of x1 plus x2 plus xn, so on. And therefore, it is equal to p plus p and is equal to np. Or it gives us the average or the expected number of successes in n trial. So, if n is the number of trials and p is the probability of success, then np is the expected value of x. In our example 2, where p was equal to 0.3 and n equal to 20, then you may find that the mean will be equal to 20 into 0.3 is equal to 6. This is interpreted as, in the long run, on an average, 6 cancer patients who undergo chemotherapy would survive after the treatment in a sample of 20 patients. We know that each of the Bernoulli variable has a variance, which we had defined earlier as p into 1 minus p. And the binomial random variable x can be considered a sum of the n Bernoulli variables. Therefore, the variance of x, capital X, is equal to variance of x1 plus x2 up to xn. And this therefore can be written as p into 1 minus p plus p into 1 minus p, so on, repeated n times. And hence is also equal to n into p into 1 minus p. Or it can be written as equal to npq, because we know 1 minus p is equal to q. So we can find out the standard deviation, and standard deviation of x, which is nothing but the under root of variance of x, will come out to be equal to under root of npq. Using again our example 2, where we knew that where we know that capital X is a binomial distribution with p equal to 20 and p equal to 0.3, we can find out that variance of x will be equal to npq, which is equal to 20 into 0.3 into 0.7, hence is equal to 4.2. And standard deviation comes out to be equal to under root of 4.2 and is approximately equal to 2.05. So we know for our current example that variance is equal to 4.2 and standard deviation is equal to 2.05. Let us now move on to another distribution, which is the multinomial distribution. We know that binomial distribution relates to the dichotomous population, which means population where there are only two possible outcomes, terms as success and failure. The multinomial distribution is a generalization of binomial distribution, which is applied when there are more than two possible outcomes of an experiment. The assumptions of the multinomial experiment are parallel to those of the binomial experiment. That means, number one, the experiment consists of n repeated independent and identical trials, which means outcome of one trial does not affect the outcome of the other trials. The second is same, the probabilities of the outcomes remain constant for each trial. Third, that each trial can result in one of the many possible outcomes. So, for example, consider n college students' preferences for 5 different newspapers. Let's call them as newspaper 1, NP1, NP2, NP5. Here, the experiment consists of recording choices of n students where each trial can result in 5 possible outcomes. Accordingly, there are 5 random variables denoted as capital Xi, where I can take the values from 1 to 5. Now we can see that in the current example, I is equal to 1 to 5. Here it means the number of students opting for newspaper NPI. Now these random variables are such that x1 plus x2 plus x3 plus x4 plus x5 is equal to n, where n is a small n. Now it is known that P1 is the proportion of students who are known to have a preference for NP1, which means they have the preference for first newspaper. P2 is for the second newspaper, and similarly up to P5 for the fifth newspaper. The sum of all 5 probabilities is equal to 1, which means we can write down that sigma or summation Pi, where I is from 1 to 5, is equal to 1. Such an experiment is called as a multinomial experiment, and the joint probability mass function of Xi is called the multinomial distribution. Generalizing the argument to R possible choices in n independent trials and applying the concept similar to binomial distribution, we can define the joint probability mass function of x1 to xr as probability of x1 to 1, x2 up to xr is equal to n factorial upon x1 factorial into x2 factorial up to xr factorial into p1 raised to power x1, p2 raised to power x2 up to pr raised to power xr. Xi, let me again repeat, is equal to 0, 1, 2, so on, with x1, x2 plus up to xr equal to n. And this probability mass function is equal to 0 otherwise. Otherwise means when this does not happen. So if r is equal to 2, it gives binomial distribution with x1 equal to number of successes, and since x1 plus x2 is equal to n, therefore x2, which is equal to n minus x1, it becomes equal to number of failures. Also, since the sum of pi's is equal to 1, p1 plus p2 in that case will be equal to 1, and p2 will be equal to 1 minus p1 equal to q. So we may say that a binomial distribution is a special case of multinomial distribution when r becomes equal to 2. Let's take an example. Say on the basis of the survey, which we have earlier said is conducted by a research company, and it was found that respective market shares of 4 newspapers NP1, NP2 up to NP4 are 15%, 20%, 30% and 35%. Suppose an investigator independently interviewed 15 persons on their newspaper preferences. Find the probability that number of persons preferring NP1, NP2, NP3 and NP4 are 3, 2, 4 and 6 respectively. You can notice that the sum total of all these is equal to 15. So what is the solution? Solution is, let xi is the number of persons preferring newspaper NPI and pi is the probability of a person preferring NPI, which can be denoted as P of NPI. And again, let me remind you, I is equal to from 1 to 4. We are given that P1 is equal to 0.15, P2 is equal to 0.20, P3 is equal to 0.30 and P4 is equal to 0.35. Then our required probability is equal to probability of 3246. 3246 is the number of persons preferring those newspapers. So this comes out to be equal to 15 factorial upon 3 factorial into 2 factorial into 4 factorial into 6 factorial into 0.15 raised to power 3 into 0.20 raised to power 2 into 0.30 raised to power 4 into 0.35 raised to power 6. If you simplify and solve this, it will come out to be equal to 0.0127. So what we have calculated is the probability that 3, 2, 4 and 6 number of persons prefer newspaper 1, 2, 3, 4, and this probability is equal to 0.0127. The question which arises now is, what is the mean and variance of the multinomial distribution? We know that the mean of the binomial distribution which is denoted as expected value of x is equal to NP. In case of multinomial distribution, if there are r possible outcomes, then correspondingly there are r independent random variables, which we know are x1 is equal to small x1 and up to capital XR equal to small xr. The respective probabilities also we have denoted from P1 to PR. Now these R variables can be considered as individual variables and therefore their expectation will be defined as expected value of xi equal to NPI, where I can take the values from 1 to R. So for the above example, which means our newspaper example, expected value of x1 is equal to NP1, which is 15 into 0.15 and is equal to 2.25. Similarly, you can calculate expected value of x2 will be 15 into 0.20 equal to 3. Expected value of x3 is equal to NP3 is equal to 15 into 0.3 is equal to 4.5, and the expected value of x4 denoted as NP4 is equal to 15 into 0.35 equal to 5.250. Now similarly, we can also find out the variance. Variance of xi earlier we had defined to be equal to NPI into 1 minus PI or NPQ. Now I again is equal to 1 to R. So what will be variance? Variance, if you substitute these values, variance of x1 will come out to be equal to 15 into 0.15 into 0.85. 0.85 is 1 minus P1 and this comes out to be equal to 2.25. Similarly, you can find out variance of x2, it comes out to be 2.4, variance of x3 comes out to be 3.15 and variance of x4 comes out to be equal to 3.4125. So let us students, after this long session, try to summarize what we have learned today in this module. We have learned about two widely applied discrete random variable distributions, namely the binomial distribution and the multinomial distribution. What we have learned is that an experiment consisting of n independent and identical trials, where if each trial can result in any of the two possible outcomes, then it is called a binomial experiment. And if each trial can result in any one of the R, where R is greater than 2 possible outcomes, it is named as a multinomial experiment. The multinomial experiment is a simple generalization of the binomial experiment, which corresponds to R equal to 2. Or I can say the reverse. You have learned that binomial distribution is a special case of multinomial distribution. We have also learned that if the voters' preferences, for example, are to be judged between two contestant parties, it would be dealt with binomial distribution. If there are more than two parties, multinomial distribution would be applied. Similarly, we have also learned that the mean and variance of binomial distribution are NP and NPQ respectively. And the mean and variance of the multinomial distribution are in vector form, which are NP1, NP2, NPR, and NP1, Q1, NP2, Q2, NPR, QR respectively.